Okay, so what we'd like to do is look at the multipole expansion of the vector potential A, and this will lead to investigation of magnetic dipoles. Recall that in the case of electric charge, we have a scalar potential which is due to those charges. It was very useful to expand those potentials in terms of a multipole expansion. Well, it's useful to expand the magnetic vector potential in the same way. When we do that, we expect the monopole term to vanish and the magnetic dipole term, which is the first non-zero term, to dominate. So here's a current loop that has current I passing through it. We'll consider this to be confined in space. One way to do that is just get far enough away from it so that it looks very small. We've written down the vector potential for various current distributions, but here's one here in terms of a line current given by this expression here, and C prime is the path over which we're integrating. R prime is the vector from the origin to this current loop, and so for example there'd be a little dl prime along the current loop that we're pointing to, and then R is coming to the field point, and so this is the source point. R is related to R prime in terms of our process by the funny R vector, which is this one here. So it points from the R prime position to the R position. And so that's basically giving us the distance from this little element here. In the case of electrostatics, what we did was we expanded 1 over funny R. And so we had an expansion which we can then use term by term to look at the various terms. When we do that for the vector potential, we get this expression here. So here's our vector potential. We're expanding 1 over R. We have the coefficient here, which is right here, and then we can bring out a factor of 1 over R to the n plus 1. So this is just the field point dependence. Then we're integrating over the primed variables, and that is this R prime to the nth power, and we're summing over n times the nth Legendre polynomial, which is right here, and then we're integrating that around the curve C. And I put a prime in there, but it doesn't matter. This is then the general expression for the expansion. So here it is again. And so we want to look at this in terms of the breakdown of these terms. So here's the first term right here, and here's the second term here, and occasionally you need more terms, but quite often this is all you need. The first term has the expression of 1 over R times the line integral of just dl. Well, if you go around the circle and just add up all the dl's, if you make a closed circle, you're going to end up with 0. So this factor right here is equal to 0. Well, this is the monopole term, and just as we said, we expect that to go to 0, and it does. Why do we expect that? Because there are no magnetic monopoles, at least that we know about. The second term is for us the most important term, and that's the dipole term. And as I said before, this will tend to be the dominant non-zero term. So let's take a look at that term. Here's our dipole. Here's just rewriting it. But we recognize that this R prime dot R hat is equal to R prime times the cosine of theta. If you look at this expression here where we have a dl in this position here, and we have R prime here and R here, theta is the angle between them, then we can take this R prime cosine theta and replace it by this R dot R hat. And that's what I've done here. So here's R dot R hat put into the interval to replace this factor here. Well, we can rewrite that in terms of looking at the expansion of a dot product, and that will be of the following form. So we can rewrite the term that we have here in terms of a term that is only R dependent and a term that is only R prime dependent. If we look at that, then this is the minus 1/2 over R hat factor, so we can start to think about the dipole. If we look at this whole system here, we can set it equal to this quantity right here. Here's the prefactor. Here's the 1 over R squared. If we identify M in terms of the magnetic dipole moment of the current loop, we can see that M is this quantity right here. it's going to be 1/2 I times r prime cross dl prime. For simple geometries, this is going to be very simple to evaluate. So one more time, we've taken this expression here and we have changed this factor here with the r squared into a m cross into r hat. Well, in terms of a current loop, if you take this current loop here, then any dl can be related to these vectors here. What I'm really interested in is the area of this region here. What I've done is put the current loop C in the plane, in a single plane, and so we've forced our current loop to be planar. So here it is again. Now we're going to have a little bit simpler expression for the dipole moment. So if we take that expression right here, so this is the one we've derived, if you look at this triangle, then this cross product divided by 2 is the area of this triangle here. And so if you just simply call that an area A, the area of the enclosed loop, then if you write m down, so this 1/2 times this is the area of the loop, and I'm talking about this area here, m will just be I times the vector A. A is the vector which points out of the curve in the direction of your thumb if you use the right hand rule where your fingers wrap in the direction of I. Let me just state that then. The direction of A, so the vector A, is consistent with the direction of the current loop. So we use the right hand rule. You wrap your fingers around the loop in the direction of the current flow, and the thumb points in the direction of M. For the above loop, if you apply that right hand rule to this current loop, you can see that M points out of the page. Here's a couple of factoids. The magnetic dipoles of a loop are independent of the choice of origin, and so you can put the origin anywhere you want, and this particular integral will not depend on the origin. Quite often we take the origin to be as I've shown it here. So for example, if the loop is a circle, you put the origin right in the center. The ideal dipole moment consists of a magnetic moment here where the area of the current loop is very, very small. And in fact, an ideal dipole moment, you let the A go to 0 and then you increase I accordingly so that the factor I times A stays constant. Normally we just simply consider A to be very small and we treat it as an ideal dipole. For just about any current loop, the dipole term in the expansion is unequal to 0. So here's a little bit of information about magnetic moments, and in particular nuclear magnetic moments. Atomic nuclei that have non-zero spin have magnetic dipole moments. Old arguments that were given for systems that might have zero magnetic quadrupole was a parity argument. So if you have a system that has parity symmetry, it implies that the nuclei cannot have a magnetic quadrupole. However, if this symmetry is broken, for example by weak interactions, then that means that non-zero quadrupole moments can occur. Nuclear magnetic octopole moments are also allowed. So dipole, octopole are allowed. They are very small, but they have been measured. In terms of nuclear moment measurements, one pioneer was Norman Ramsey at Harvard, and he got the Nobel Prize in physics for a lot of this work. His work has led to using magnetic moments to generate atomic clock devices. And what it does is uses transitions involving reorienting the nuclei in the B field that is interacting with an external field and generated by the atom and molecule electrons. And this has led to another system, a nuclear magnetic resonance type of measurement, and MRI, which you're familiar with. Nuclear magnetic resonance, NMR, is used quite frequently as a characterization application, and it's most commonly used in chemistry and on biosystems. And what we're really talking about is biomolecules often crystallized into a crystal to give better information. When NMR is applied to imaging, it's called MRI. And the reason is because the word nuclear is scary, and so the people who were making these devices changed it to magnetic resonance imaging. It's still nuclear, but it's MRI. So what it is basically NMR using very fancy magnetic fields that can be scanned with very high precision. The nucleus that's being imaged is hydrogen, and that of course is contained in water. So if you have organs and systems like your brain and perhaps your knees or some other part of your body, the distribution of packets of water, so here's something where you have packets of water, then they will become bright when you do the NMR or MRI of those structures. So that's how you see inside your brain and so on. Now that we have the magnetic potential, so for example just the magnetic dipole term, so we're going to assume that we have a pure magnetic dipole M, and it's located at the origin. So in other words, R prime is 0. So here it is right here. Here's our R going to our field point at R. So one more time, the source point is the origin, and so that's where we place our magnetic dipole. To save ourselves a lot of work, we're just going to orient that along the positive z direction. So then theta is the angle to the r vector, and if you remember, so the little r hat is in this direction, and our theta hat is in the direction of increasing theta. So I've drawn it here as a little unit vector. If we take our A dipole and take the cross product, that'll give us a sine of theta, and this of course, when we do that, we're going to get a phi hat direction for the vector potential. So don't forget, this is a vector, and we have it as a single term in the cross product, which is in the phi direction. I've shown that direction here. So if M is oriented as we have here, the phi is given by this angle here, and phi hat is in the direction of increasing phi, so it goes in this direction here. Well, that really simplifies our calculation of B, because we're just going to take the curl of A, and A is simple, so that when we first of all separate out the constants here, and then we just have a single term in the curl, which is given by sine theta over r squared, and it's operating on this component here. It's easiest to do this curl in spherical coordinates, so I'm just going to call this f of r and theta just to show you how to get started. You go and look up the curl of a function, and the function has a phi component, and so what you find is you have 1 over r sine theta partial with respect to theta times sine theta f of r and theta. All of this is the r component of the curl, and then we go to the theta factor or term, and that is the partial with respect to r of r times f of r theta. So putting in our f of r theta and taking the derivatives, what we find is that the dipole, the magnetic dipole field, is mu 0 m over 4 pi r cubed. So this is the magnitude of m right here. And then there's an r hat term, which is 2 cosine theta, and there's a theta term, which is sine theta. If you look at this in terms of what we saw when we did the electrostatic version, so we were doing the potential of a dipole, it's precisely the same form, except we replace mu 0 m with the electric dipole over epsilon naught. In other words, these two have the same functional form with just a replacement of this little region here, this constant. So what does that look like? We looked at the E field earlier, so here's the E dipole, and this should be, this should be epsilon naught here. So that's K if we take 1 over 4 pi epsilon naught. If you plot that, here's the ideal dipole, which is equal to Q times D, where D is really, really small, and it really should go to 0. But what I show here is a Mathematica plot of that function. What it looks like are loops, but realize that for a real dipole, these would be coming in to the plus minus charges that are, infinitesimally apart. They do end at the position of this dipole, and they start there also. So that's the difference between electric field case of a dipole versus a magnetic case, which we show here. These are the functions that we're plotting. This is E dipole, and this is B dipole. And these types of plots are called the streamlines of the vector field. So if we now do the magnetic field, this figure is from Wiki, then it's for a finite sized current loop. So remember, what we have is M equals IA. This is almost ideal, so you make the A very, very small, and it really should go to 0 for an ideal magnetic dipole. Here the field lines are in fact closed, and in principle, as you go closer and closer to here, you'll still have closed loops, because you can't have a source and a sink for the magnetic field, because divergence of B equals 0. So you can see that these are very similar in shape and form, and in principle, if you took a point out here, and the way I plotted this, they don't look like circles. If we did a careful job, they would be circles. Let's look at an example. And this is sort of a classic problem of changing the expression that we have for B field in terms of coordinate-free form. So the form that I have here does not depend on whether we're in Cartesian, spherical, or cylindrical coordinates. We did this for the electric dipole, and again we got the same sort of function. We align M along the axis again, and we have our theta and R as drawn here. The vector from M to the field point will be R, and the R prime is equal to 0. Since we're in the plane, we're only going to have R in the plane, little r hat, and here's theta hat right here, perpendicular to R. This angle here, if this is pi, the angle that's between the z-axis and R hat, that will be theta, and this is pi over 2 to get you the entire distance here. So here's the scalar product, m dot r hat. We know that if you look at the equation for z dot r hat, you'd have the cosine of theta, which is the angle between those two vectors. That's m dot r hat is equal to m times cosine theta, because the length of r hat is 1. The scalar product of m dot theta hat is going to involve this angle that I told you about here, and so we'll have m times the cosine of that angle. And remember, that just has to do with taking a cross product. And so if you look at the expansion of cosine pi over 2 plus theta, you get minus sine theta. And so our dot product of m with theta hat is equal to this. We write down the expression that we derived for B. This is what we derived. So we have the prefactor r over cubed, and then these factors here for the two components. If we write these in terms of the two dot products, so you'll notice that we can replace m cosine theta with m dot r hat. We can replace m sine theta with basically minus m dot theta hat, and we'll end up with the equation that we have here. Think of it this way: we've done this replacement and we've done this replacement, keeping track of the signs. To get the equation that we want a 3 here. So we're going to simply add one of these and subtract it. And that's what we have here. 3 times this combination here minus 1. And that'll give us the 2. And then we still have minus m dot theta hat. What we're doing here is we're finding the rth component of m. And that's m sub r. If you look over here, this is m theta right here. And so what you have then is mr, r hat, and then minus, oh yeah, there's a minus sign here, minus m dot theta hat, which is m theta times theta hat. Well, that's how you define a vector, which would actually be our m. So minus m. That's just looking at the components and the unit vectors of the vector. So putting that back in here, if you look at our expression, then you can put in for the minus m here, you'll have 3 times m dot r hat minus m. And this is coming from this combination right here. So here's m dot r hat right here. Here's m dot theta hat right here. And so we can just replace that last set of terms with a minus m. And that gives us the expression that we wanted. Just to remind you, the way we got this was through the expansion of A. And if we're only going to look at the dipole term, then what we're doing is looking at the case where r is considerably larger than the size of the dipole. So pi s squared is what we call little a. So if m is equal to I times little a, this equation holds rigorously for very large distances away from that little area, and so that means r is much greater than s. Well, here's another example. Let's think of a square loop that's 2a by 2a, and it's in the xy plane centered at the origin. And we're to find b on the z-axis for z much greater than a. What we're saying here is that we can use the equations that we've developed. For this case here, where we have z greater than a, we can use the dipole approximation so that for m equaling I times a times a unit vector k, this will be I 4a squared times unit vector k. M is along the z-axis and points up. What we're talking about then is a square loop like this. The sides are 2a and 2a. We put the origin right in the center, and we're thinking about finding b along the z-axis here. Z is much greater than the size of one edge of the loop. Let's use our equation that we just developed here. So if you look at m, which is equal to m times z hat, so I'll just draw it here. This is m, oriented along the z-axis. Then that'll be the magnitude of m times z hat. R hat is the unit vector pointing towards the field point, so that'll be z hat, because the point we're interested in is up here on the z-axis. So then we can substitute these in for b, and so if you look at m dot r hat, it's going to be m z hat dot z hat, and so that'll give us the scalar 3m and then times the unit vector r hat, and that's what we have here. So this is the first term evaluated for our simple case of m oriented along z and r hat oriented along z. Well, the second term is just to write m. M is just equal to m z hat, so with the minus sign we get this term here. Well, this is trivial. We can add these two together, so we get 2m z hat multiplied by the prefactor. So basically this is the answer right here. So we have the b along the z-axis for this small dipole oriented here. So if we want, we can put in m in terms of the dimensions and currents that we're representing here. Remember, current I is in this direction if we want the dipole in this direction. Just substituting that in, we get this in terms of I and a, the side of the square. Well, this is another example where we're going to find a magnetic dipole moment. Consider a flat disk which has a surface charge density sigma, which is uniform. So that's sigma on the surface here. And it's rotating at a constant velocity. So let's take this direction here for the omega, and so that's the angular frequency of the rotation. The outer radius of the disk is capital R. If we consider then a ring of charge, we can find the dipole moment of that ring and then just simply add them up as we go from 0 to capital R. So let's consider the inner radius of the little ring as r, and the outer radius would be r plus dr. So the width of the ring is dr. The charge on that ring, which we call dq, is just sigma times the area of the ring, which you can see here is pi times the outer radius squared minus pi times the inner radius squared. If you expand the square here, you get r squared plus 2rdr plus dr squared. We're going to throw out the dr squared term, and you'll notice that we get a pi r squared being canceled by this, and so this is approximately equal to then 2 pi sigma r squared times dr. Now it's rotating, the disk is rotating, so the charge is rotating, and that moving charge corresponds to a current, and we'll call that di. And so we're going to use the fact that dt is the unit of time. It's just going to be the time for one revolution. So we'll make it 2 pi over omega. So that means then this di is equal to dq over dt. So if we take our dt, which is 2 pi over omega, remember this is just the period of rotation, so that's why we use it, 2 pi over omega. And here's dq that we derived above. So taking that ratio, then we'll have sigma omega r squared dr for di. What's the dipole moment? Well, the dipole moment is equal to dm times di times the area. And so this will be equal to the di that is right here times pi r squared. This is in the z hat direction just simply by the right hand rule. Here's our pi r squared, here's our di, and so we collect terms and we have, cancel this, we have pi sigma omega times r cubed dr z hat. Now we're ready to integrate. So this is our dm, we integrate dm, and so this is equal to the constants pi sigma omega, integrating r cubed from 0 to capital R. Final result then is pi over 4 sigma omega r to the 4th z hat. And I guess the only thing to say is that the more charge you have per unit area, or the faster you turn the disk, or the bigger you make it, you get a larger omega, or m, excuse me. When I said that, I was keeping one constant while I look at the other one. If you change them all, of course, you can get another kind of change. Here's another example. We're given a magnetic dipole. This happens to be pointed in the minus z direction, magnitude m0, so the minus is in the minus direction. It's located at the origin in a uniform field, so otherwise uniform field. So here's that value, and it's pointed in the plus z direction, so these are opposing each other. What we want to show is that there exists a spherical circle centered at the origin through which no magnetic field lines pass. And this crazy word spherical circle means that if we stay in a plane, it looks like a circle. We write this down as a combination of two fields, so we add them up to get B total. Here's the B0 term, which was given up above. And if we take our dipole heading in the minus z hat direction, then we look at the field due to a dipole that we had before, but we just put a minus sign here. And we'll use the form of 2 cosine theta sine theta for the angular and radial dependence. In order to get this simplified, we want to add these two terms. It's easiest to change z hat into a expression of r hat and theta hat dependence. This is given in many tables that the z hat is converted to these two terms here if you go to spherical coordinates. And so you have the cosine of r hat minus sine of theta r hat. And you'll notice that because this is a unit vector, we don't have any magnitude here other than the trig functions. I guess if you were to dot this into each other, see that you get cosine theta plus sine squared plus sine squared theta, which would give you a 1. So let's substitute into B total now, this z hat. And so we combine the terms that have a r hat dependence, and that's what we have here. And then we do the same thing for the theta hat terms here. It's complex, but what are we going to do? Well, if you look at this condition where you have r equal to some r circle, we want the r component of B total to go to 0. If we can find that, we're done. So you set the r component of B total to 0 and see if you can find an r circle. Well, you can see that's going to work because we have this factor here times the cosine theta is equal to 0. So all we've done is taken this factor right here and set it equal to 0. Well, you can see that we can solve for r circle. This is r cubed, so we're going to get 1/3 power for the whole thing. And we're left with mu0 m0 2 pi b0 to the 1/3 power. So we indeed have found an r circle. The fact that if we have this equal, then b sub r is equal to 0, which means that at any theta and phi, because there's no dependence on these parameters, there's no field lines which cross the spherical surface because BR is equal to 0 on that circle. What does this look like? I've taken Mathematica, and to use the vector field plot, which I've shown down here, you have to do this in Cartesian coordinates. So I've taken our result and changed it to Cartesian coordinates. To plot it, I've set the constants that we have in the problem all equal to 1, and so here's the expression that we're going to be evaluating for this circle, and to get a numerical value, this function n is applied. So here's the plot. All these arrows here is the combination of B0 and the dipole field. So I've shown you a dipole right here, and I've shown you the z direction for the external field. And what you see here is that out here there's lots of B vectors. They're all headed uniformly in the z direction. Where the dipole is, we're going to get field lines that go like this. And so we add the two fields together, and what you find is that on this circle right here, we're satisfying the fact there's no R component to the field. We indeed have this case where we don't cross this line here. I wasn't real careful about where I put that circle, but I think you can see these vectors want to go to the tangent to this circle, and the same goes for over here. This in fact is very, very close to showing you that if you add these two fields, you get this circle where you don't have lines crossing. The only way this could happen is that these two are directed in opposite directions, because if you put this in the other direction, you'd have lots of addition all over this region here and never get this radial component to disappear.